going. Oops, got to find my presentation here. So we're gonna have a quick stretch break for 15 minutes. Please do go grab your lunch. We will have a presentation when we get back from Amy Shallcross, and we'll see you in just about 15 minutes.
Generation, power generation, both hydropower and thermoelectric. Now, the issue is that all of these things either require water or a space to store water. And we only have finite resources to do so. So nature gives us precipitation. We have about 11 major reservoirs, and then, or you can have a runner, use the water run of river. So I mentioned storage. So to meet the goals of the basin, we basically have 11 major reservoirs, and they are different types of reservoirs. So we have 2 hydropower reservoirs, which are very old, built in the 1920s. We have some federal reservoirs built in the 1960s and 70s. We have a hydropower reservoir. It doesn't generate hydropower, but the the power facilities can use that to make up for their consumptive use, so they can still take water in a drought condition and not have to cut back. Basically, these 11 reservoirs are in our drought management program, and then we also have permitting programs to limit water use and also to look at water quality. So I mentioned the different types of water users. These are the major purveyors in the basin. In Pennsylvania, we have several. They have several purveyors along the non-tidal main stem, and then Philadelphia takes water from the estuary, from the more freshwater portion of the estuary. Previously, Chester, Pennsylvania had an intake on the Delaware River, and they abandoned it in the 1930s after a really bad salinity intrusion event, which we'll talk about later. In Delaware, Newcastle County, they had a water intake on a tributary, and they ended up, because there was too much salinity coming upstream, they ended up installing a inflatable dam so that when the water gets really saline downstream, they can put that up and sort of prevent the upwards migration of salinity. So Alan talked about New York City, and basically in New York City has to supply water both for the city and communities along the aqueduct that takes water from the Delaware River Basin. And then New Jersey has both a non-tidal out-of-basin diversion based on a decree, as well as New York City. And then it also has a tidal intake, and both the Philadelphia and this New Jersey intake right here, they're across the river from each other. And that's where the tidal river, they take water from the tidal river because it's most of the times fresh. We have some other water users in the basin. You can see these blue dots are all along the river, and they are different facilities. The blue dots are surface water facilities, and if these facilities aren't taking water from the river, they would probably be taking water from Philadelphia or one of the other water utilities, either groundwater or surface water. So on the upper left is the Philadelphia's Baxter treatment plant. On the right is Evonik's Specialty Chemicals. On the lower left is Kimberly-Clark. They make all the paper products. Remember, toilet paper was an issue about 3 years ago. And then we also have the Salem Nuclear Power Plant in the estuary. So all of these uses are very important. Now, I mentioned salinity when I talked about Philadelphia's intake, and salinity is a really big issue in the estuary because obviously it's where saltwater and freshwater mix. So this is a picture of the 1960s drought. This is at the head of tide. So this is just at the top of the non-tidal river before it goes downstream into the estuary. In the 1960s drought, there are extreme flows. There were less than 2/3 of the current minimum flow after regulation. There was actually in a very extreme condition. There was insufficient water for New York City to take its out-of-basin diversion. At the 1965 drought hearing, there were many users that came in and talked about the damage to their equipment. One utility, I think it was actually, Kimberly-Clark, they had $5 million of damage in 2019 dollars. $5 million of damage. The high salinity water, like almost like unusable water, was only 8 miles from Philadelphia's drinking water intake. Their commissioner came and spoke at that hearing. And some studies have actually estimated this drought as a 250-year drought. So in order to manage drought conditions, we have a drought management plan, and the goal of the drought management plan is to preserve regional storage and repel salinity. Basically, we're balancing storage in the reservoirs for different purposes, like New York City's water supply, but then storage in the storage in the lower basin, which we use to repel salinity, which I'll discuss in a minute. So some aspects of the drought management plan were the drought of record was declared to be the planning standard for the basin for permitting, particularly NIPD's permits. We have phase reductions in flow objectives that exports out of basin water and conservation releases. When salinity gets really high, we actually start to increase the flow objectives again, sort of like we're saving water for a non-rainy day. We have water conservation requirements, and we permit consumptive use. That's the amount of water that doesn't get back into the river. One of the recommendations was to develop additional storage, but only 1 of 5 projects was actually developed. I want to mention that this plan was established more than 40 years ago. And so it's really important that with climate change, we start to revisit it. I talked about the drought management program because even though there are lots of ways that the Delaware Basin will be impacted by climate change, storm surge, more hurricanes, weather, habitat, high tide flooding. I think some of the areas in the river actually will experience like 180 days of high tide flooding. Then you have sea level rise, snowpack and ice, and then drought. I'm going to really just focus this presentation on drought, basically the water availability and salinity issues. So basically, I pulled this together for a different presentation, but it's appropriate for here because these are the, people have mentioned what questions are you trying to answer? So we're trying to answer, how does sea level rise affect salinity? How much water is going to be available? Do I need more storage? What about water use? And then we need hydrologic models, operational models. That's reservoir storage, how you use reservoir storage to meet those flow objectives. Hydrodynamic, we need that for sea level rise and water quality. And we also need expertise and resources, which someone mentioned that, we have a lot of places have small staffs. Their staff get pulled for different reasons, for different purposes, different projects. And that's like, what we need is dedicated staff. Otherwise, you have to go out to a consultant. So I think what's problematic about climate science for us is generalizations that have been made about the basin or about the Northeast. Warmer, wetter, we're going to have more flash droughts. There's a lot of uncertainty about whether or not we're going to continue to have the tropical storms. That's somewhat problematic. Then we hear stationarity is dead or undead. I'll talk about that in a minute. The GCM and RCMs, they've already talked. Abby and Dan already talked about some of the issues with those. We have I mentioned we have the need for the hydrologic models. The scale of our basin is 13,000 square miles. That's a lot to have a really well-calibrated hydrologic model. And then also, I think we have some, problem communicating results to different audiences. Try to explain uncertainty, risk, and timelines. And also in some ways, like probability is math, right? You're doing math on your model results to see where everything fits. Is it probability? If you've ever looked into some flood frequency statistics, they basically say, we always talk about the 100-year flood, and we tried to move to a 1% chance of occurrence. But if you do the probability analysis, basically it means that during a 30-year mortgage, you have a 25% chance of having a 100-year drought or living through a 100-year drought. So basically, I think sometimes communicating risk using probabilities is a little difficult. So I mentioned stationarity is undead. We use all these, we want to use this model in climate science, but also there's a lot of value in looking back at historical data and using that. One thing is it's proof that a storm or a drought period is possible. Like it's proof that the lowest flow in the Delaware River has been this low before. We can use past data to assess vulnerability, especially if your programs don't necessarily do what they're supposed to do. Another thing is with historical data, we develop model parameters, we ground truth the model. We use them to calibrate models, and then also you could use those for a Monte Carlo analysis, which is really a statistical type of analysis. But even though I'm talking about stationarity, we really need to do it. We want to combine that with different climate science, basically to do a top-down and a bottom-up analysis to basically get the big picture. So Dan and Abby were talking about what's going to happen in the future. The climate basically is kind of the average of the weather, right? And then if we want to look at kind of like we design things for the weather, the 100-year storm, the 250-year drought. And so how vulnerable are we? Like we need to look at what's happening with our aging infrastructure and do one thing we're doing is we're trying to see if our existing programs work. There is a flood mitigation plan in the basin. Is that still going to be valid if the seasonality of flows changes and snowpack? So we're looking into all of that. Oops, I think my slow messed up. So one of the messed up my 2 slides. Sorry. One of the issues confronting us is sea level rise and salinity. And if you look at the diagram on the right, basically it's sort of like looking at the estuary as a bathtub. And what you have is on the left is the Atlantic Ocean, or the bay, and then on the right is the flow coming downstream. So currently, we have, a certain amount of force from the ocean coming in and a certain amount of dilution and force from fresh water coming in. If we have sea level rise, that bathtub gets deeper and the force of the ocean coming in is much greater than the force of flow coming in. And so the higher salinity water can move upstream. We use something called the salt front, which is where the concentration of chlorides in the estuary is 250 milligrams per liter. And that's based on a previous public drinking water standard. And you guys know this more than me. So basically it means that you're going to have taste and odor issues. Now, just going back to stationarity for a minute here. So we looked at, even though we're doing a hydrodynamic model, which I'll talk about, I went back and I looked at what were the worst salinity intrusion events in the Delaware estuary. And the graphs on the right are basically the 30-day moving average flow entering the estuary from the non-tidal Delaware watershed. And the black line is where the salt front was during that period of time. And the red line is basically near the Schuylkill River, which is one of the goals. We'd like to keep the salt front below the Schuylkill River. And here you can see the Schuylkill River is down here, and the highest upstream location of the salt front was near the Ben Franklin Bridge, and it was only 8 miles from the drinking water intakes. Anyway, so you can see here that these are all the fall months. And this is when we would usually late summer and the fall. Usually we see salinity intrusion basically usually it's after September. And what happens is, flows are lower during that period of time. But then one other aspect is the tide changes over the year, like the mean sea level is not really constant over the year. What you'll see is the tide tends to be much lower in the winter time and higher in the fall. It has to do something like where the moon is, and I'm not really sure, but you can see here that in the fall, when you have a sustained period of low flow, the salt front starts to move upstream. And what we've seen is that when you have 30 days of sustained low flow, particularly around 2,500 CFS or less, then we will start to see really bad salinity intrusion events. And like the only reason why the salt front in 1965 didn't get up as high as say 1964 is that they had this storm, this like brief period of higher flows, and then they start to get really high. Now you notice that these flows in the 1960s and 1957 had the higher salinity intrusion based on the salt front. But if you look at 2002 and 2016, these flows were higher than 2,500 CFS, and that's because of the drought management program. Oops, I think I saw this. Oh, I guess I had that slide in there twice, but the question we're trying to answer is how far upstream are we actually going to get with sea level rise? So to answer that question, we developed a three-dimensional hydrodynamic model. We call it SM3D. It was actually built with the same model code that Philadelphia built their model. Our model is focused specifically on salinity. A three-dimensional model is required because of complex physics and hydrodynamics that occur in the estuary. Particularly, one thing in the estuary is it basically turns into a funnel, and so there's a lot of issues related to that. Basically, I would say there's a lot of data and not a lot of data to calibrate the model. We have some major inflow called the C&D Canal, which brings water from the Chesapeake to the Delaware. Just recently, they started monitoring that. Anyway, so and then the models are also computationally intensive. It takes us basically a weekend to run a year worth of data. And I guess I just included this here because you can see that in the Bay Area, the flow, the salinity is really stratified. This is where the Bay is. And these are salinity, and you can see that the salinity is really stratified near the ocean, but then as you get upstream, it becomes more consistent, and that's related to density-driven hydrodynamics, temperature differences, and those sorts of things. So we constructed this model, and one of the interesting results, and it's coming up in the Mississippi issue related to salinity moving towards New Orleans, is the majority of, we say the majority of, but a significant amount of salt is transported through the Federal Navigation Channel in the Bay. And basically, so that was I think we knew this, but it was an interesting finding. This is sort of how, actually this was supposed to be the change in salinity in different locations of the river. And basically we do model the salinity chloride profile so that basically the model is well calibrated. So we use that model to assess kind of like the range of where salinity would occur, that high salinity water would occur under different sea level rise projections. We use 10 years of data, mentioned, it takes a weekend to run a year's worth of data. And those years were representative of the entire flow record of the flow at Trenton. And then you can see here that this is the mouth, the mouth of the Schuylkill River. And you can see that, we will get exceedances, we will get intrusion above the Schuylkill River. This is actually in 1960s, the sea level rise was much lower. So our baseline is 0 meters. So we do see intrusion above the Schuylkill River. And then basically, once you get to 1.6 meters of sea level rise, you're almost, basically, it's just outside of normal conditions when you would be above the Schuylkill River. Some of the planned and future analyses we have related to sea level rise are basically looking at that, the Trenton flow objective, like how much flow is getting into the estuary. And then also, are there alternatives to the Trenton flow objective that will help us manage salinity better? Like some is looking at, so the flow objective is a constant flow, but there's also pulses, locations where you might increase flow. There's, depending on the source of water, you are able to push salt downstream a little differently. And then there's also timing of changes in the flow objective. So those are potentially some issues that we might look at. You know, other conditions, once we develop our climate impacted flows, we would use those to see how different they are from basically the flows that we've used. Tides, right now we're currently using, you know, the 1965 tide for the extreme analyses. We want to look on possibly generating an even worse tide. We did do a Monte Carlo analysis with a simplified model, and we're looking at the worst flow tide combinations. Another thing that's going to happen is it looks like trend analysis indicates that the chlorides from the non-tidal river may double by 2060. So we're also looking at doing that. And I left the numbers off this on purpose, but basically what we're doing is we're looking at sea level rise and how much flow would you need to keep that high salinity water below the Schuylkill River. And so those are one of the types of analyses that we're working on. So in terms of the climate assessment, we've done two separate analyses. The first analysis, am I running out of time? The first analysis.
5 minutes, Amy.
Okay, okay, this is good. So the first analysis we did, we used a hydrologic model developed by the USGS. It was developed as part of the Secure Water Act and the Delaware pilot of the water census. To get climate, they used the delta factor method with an adjustment for evaporation. And basically, I guess they found that the evaporation was too high for, you know, when they ran it with the temperatures from the climate models. And so they created this temperature adjustment factor. I think it's called the Priestley-Taylor. The problem with this analysis was it was based on available data from PRISM. So it only looked 30 years back. And 30 years, I mean, actually, it looked forward into 2100. But because you're scaling precipitation, because it didn't have the drought of record in there, I didn't get a worse drought of record, and I sort of got laughed out of the room. So basically, we had to go to another analysis. One of the other aspects of this is this model only ran on one computer. The USGS had some kind of software on their in their Esri enterprise software, that some kind of aspect of it that we couldn't figure out what it was. So I begged, borrowed, and someone gave me a hard drive from USGS. Basically, I stopped counting it after 18,000 hours of computational time. It took me a long time to run all the simulations. Well, then we ran them through a water supply. Oh, and then we basically looked at what the potential change in reservoir inflows were. And you can see the seasonality of those changes. So after we ran it through the water supply planning model, I basically say that the results were anticlimactic, basically because they were inconclusive, whether either which RCP, GCM, and there was no worse drought. And our conclusion was that we needed to look at GCMs with hindcasts, including the 1960s. And then we also need to pursue sea level rise, although I talked about that first. So one of the things that, so then we looked at another project where we started to look at higher resolution models, a program called Cordex. We used bias correction called quantile distribution mapping. And we had a different hydrologic model. We had issues with that because it basically just didn't capture the full range of flow. And basically, but we do have now a process for additional analyses that we can use with different climate models. We have this whole like hit run, and it'll run all the way through our water supply planning model. But some of the issues that we found were like the state of the observed data. We had to do a lot of QA and cleanup of the observed data to kind of do the bias correction. And then also I mentioned the hydrologic models. But one thing, so I think that Julia and Dan and Abby mentioned the drizzle days. So when I looked at the raw GCM precipitation versus the observed precipitation, there were 15 more inches of precipitation, which is 30% more precipitation. I don't feel good about that. You know, I'm using a model to kind of tell me how climate changes, and it gets the precipitation wrong 30% of the time. And we went back, and we had accounted for drizzle days, but that only explained away 3 inches of precipitation. So I don't know how we feel about that. And we need to talk to like Dan and other researchers to see what they think. So now I'm done. So basically for our analyses or climate analyses, we're going to take that top down and bottom up approach. We'll look at vulnerability, like what situations cause issues related to drought in our basin. We're going to continue to refine our tools as we go and as more data becomes available. One problem that I didn't mention is I think that there's a real problem looking at uncertainty and defining risk and explaining that to decision makers. Like, what do I do? How do I combine where sea level rise might be and the probability of seeing a different flow, right? And so how do those interact? And then we want to do more collaboration with stakeholders. I think New York City and DRBC have been talking about different ways to collaborate. And then we also are working with Philadelphia related to some of the saline modeling. And so, or basically kind of comparing our saline modeling. And so, that's where we would really like to expand our analyses. And then one other thing is that I mentioned stakeholders. Before we do any other planning analyses, we want to meet with our advisory committees and talk about different assumptions that they would like to see in our plans. Okay, sorry, that's it. And then here's just a nice picture of ice on the Delaware, which we may never see again. No, just kidding.